welcome to this class, and we are going to discuss now the polar encoding part. Okay, and this will be similar to LDPC, wherein we understood only the few key ideas which are required for us to understand the complete chain with respect to the polar encoding. Okay, that's what we did for LDPC encoding. We did not go into the details of LDPC encoding. Okay, so that's what we'll do here. We'll again understand few key ideas about polar encoding. Okay, now this is what it is. That's the every step, every block is designed to basically reduce this pain. Okay, and we'll try to understand it. And these are the few key references which discuss these polar decoding or polar encoding decoding principles. Okay, if you are interested, you can check these papers. Okay, okay, so this is the PDCCH chain. Okay, and we'll keep talking about it in the subsequent classes also. And as I said earlier, in this chain, polar decoder is the most complicated block. Okay, so we have the DCI, and what we have learned till now is this 24-bit CRC gets appended to it. The last 16-bit of this CRC gets scrambled with the RNTI. Okay, and that is done because UE has to perform blind decoding in order to figure out whether this DCI has been transmitted or not. Okay, and it can make X possible maximum attempts. Okay, so and that depends on the subcarrier spacing. Okay, but the number of attempts is restricted. Okay, now so the first module which we are going to see, I'm going to skip the CRC interleaver for some time. Okay, we'll come back to it. Okay, but first we'll understand this polar encoding. And then, of course, opposite of it, that polar decoding has to be done at the receiver. Okay. Now, the standard, the polar coding block consists of these three different modules. Okay. And why this interleaver is there and why this interleaver is there, we'll understand that in great detail. Okay. But let's first try to understand this. Okay. Right. So, what are the key features? Just to recap, polar decoding instead of LDPC decoding is done because it can give low BLER at short code block length, and DCI payload is extremely small when compared with the data payload or PDCCH payload. Okay, right, and these are the key requirements: low power and hardware consumption for PDCCH decoding, and that's the blind decoding user has to perform. Okay, right. So as I said earlier, battery and the mobile should not run out of battery. Okay, right. So keeping this in mind, let's try to understand how this polar encoding is designed. Right. So first thing is, what is N and what is K? Okay, so N is the output, right? Okay, and K is the input. So that's a polar code of length. N is equal to, and if you look at it, the polar encoding length is N. Okay, right? And what is power 2, right? So what it does is basically the output is N. Okay, it will give you N bits. Okay, right? What it creates is, and it creates N virtual channel. What is the data is going to go through the our noisy channels. Okay, and what am I saying here is that you decode, you take in N bits, right, and then polar decoder will decode it, right? Okay, that's the idea. Now what happens is, the way it is designed, that polar code, the way it encodes data, it tries to create these N virtual channels. It's a philosophy. Okay, right? You are passing on these bits, N bits. Okay, and the encoder is going to encode that these N bits see different channels, and through each of this channel, a single bit is transmitted. Right? So there are N bits. Polar encoder is designed such that it creates N different channels. Okay, and through each of this channel, a single bit is transmitted. Right? And each of this bit channel, there are N of them, has a different reliability when it goes through the actual channel. And what is the actual channel? The noise gets added. Right? So encoder has artificially created N different channels. Okay, and each of this channel has a different reliability, right? And what are you sending? You are sending data bits and parity bits, right? Okay, so let's see that. So what is this? Okay, so the message bits, we are calling it K. Okay, so that B has become K here. Okay, so that I think that's why it was there in the last class also. So message bits are allocated K is equal to A plus L most reliable channels. So what are we doing here? What is the length of the message? Capital K. Okay, that B has become K. Okay, no confusion. Okay, so what are we saying here? That this A plus L, so each of this sub-channel has a different reliability. So what will you do? Because your data has to be communicated reliably, right? So what this encoder does is, take out of these N channels, it assigns this capital K channels to the data bits. Okay, they are the most reliable sub-channels. Okay, right? So that's what it does. And order of reliability of the bit channel depend on the channel condition and the code length. What are we saying here? That channel condition, how noisy it is. Okay, if the channel is so bad, okay, all these sub-channels will have poor reliability. Okay, right? Plus the code length, higher the code length, more reliability these sub-channels will have. Of course, it is working better, the code is working better, right? The more the number of parity bits, more, and then it will be like the data will be, like the coding will be better. Okay, coding will be, gain will be higher. Okay, but the philosophy here is the way it is designed. Okay, it was conceived like that basically creates so many virtual sub-channels. Okay, each of them has a different reliability, and assign these message bits to the most reliable channel, right? And there are multiple methods for designing this reliability pattern for fixed code length. What are we saying here? Okay, if n is the output length, okay, k is the input, there are multiple ways in which these reliable patterns can be designed, right? So, and that's our IP, and people have patented these reliability patterns and they try to push into the standard, right? So it is not necessary that the most reliable, the best design comes from the standard, but one of the best designs. And as I said, there are different reliability patterns corresponding to fixed code length. Okay, right? And standard provides this reliability pattern as a part of the polar encoder. If you are working on polar encoder, you will see that these reliability patterns are given to you, and you can design the polar encoder accordingly. Okay, right? So how is it done? Okay, so this is the philosophy. Okay, that polar encoder creates these virtual channels and assigns these k bits to the most reliable channel. That's all. And then it is an encoder at the end of the day. What it has to do, it has to take these. Okay, what is happening here? Okay, the code word D, this is the output. How is it calculated? U is the input. G is a transformation matrix, something like the parity check matrix, which we saw for the LDPC. Okay, right? So what is this? You see this G of n is like n cross n matrix, right? So what is happening here? This U has also should be, it will not be k, it will be n. The input also is n, capital N. So what is happening? So what are we saying here? Okay, look at this equation carefully. D is the output, which is of n length, n cross n matrix. What will be the length of this? It has to be n cross 1. And then 1 cross n, that's how you can multiply it. Okay, right? And but how do you create this U from, from this k length DCI? What is the length of DCI? Capital K. Okay, but you need to feed in capital N input. Okay, so you need to create this U. Okay, so what is this? So these indices, so what are we saying here? You take some vector, capital N length vector, okay, then divide its indices. That's the encoding process. Okay, you divide its indices into two sets. And what are those two sets? K size information indices, which is of set I, okay, and what are this? N minus k size frozen indices. These are technical terms which the polar encoder uses. What are we saying here? What is the process we are doing here? We have a k length DCI, okay, which needs to be fitted into an n length vector, correct, and so that it can be encoded. Okay, now these indices, okay, they are divided into information indices I. What will be the length of those indices? How many such indices will be there? K, because the k is the information size. And what will the length of the remaining indices? There will be n minus k, and they are called frozen indices. Okay, right? So if the index I, if it is a frozen index, make it 0. That's what I am saying. Okay, right? And store information at other indices. And this index set is given to you, and this is directly connected to the reliability pattern. That's why I introduced these terms. Okay, right? So what is this? You understand what are we saying here? Okay, that polar encoder has been designed to create n virtual channels. It takes in n inputs and gives you n outputs, because it has to create n virtual channels. Okay, now how do you create this vector U, which is an n length vector? This is basically this n length vector is divided into two different kind of indices. One is information index, other one is frozen index. Okay, and of course this information index are coupled to this reliability pattern. Okay, because you are going to assign, these indices will be such that they pass through the most reliable channel, right? Okay, so that they get, their corruption is the minimum, okay, when they pass through the channel. This is the overall philosophy. And the reason I am telling you this is because you start reading the standard, they'll give you this information index, they'll give you frozen index, they'll give you this reliability pattern. Okay, so with this you will understand what is happening in the polar encoding block, right? So that's one thing, and this is what we require. Okay, we'll use these ideas later also. Okay, but this is the broad knowledge of the polar encoding we require. But what is this? What is the key idea here? Okay, better than LDPC for short input length, right? It provides lower BLER at the same SNR. Fine, okay. Minimum code rate is 1/8. That's another difference, 1/3. Why it should be 1/8? Because we have to understand this. Okay, these control bits are more important than the data bit. Okay, relative importance. Okay, right? Whether you are able to decode data or not. Okay, initially you should be able to decode the control information. Okay, so you'll essentially see that the PDCCH is encoded at a rate which is lower than your PDCCH encoding. Okay, because you want to give more protection to that, and that's the key idea. If you are talking about 1/3 there, we are talking about 1/8 here. Okay, right? And lower or higher rate, again, they are achieved using rate matching. Okay, certain subtle differences between the rate matching and PDCCH chain and PDCCH chain. We'll see that also. Right? Now, mother code is limited to power of 2. N is equal to 2n. Mother code basically before rate matching. Right? That's what we call as the mother code, which is the output of the encoder. Right? Okay, that's limited to. This is a restriction. Okay, this limited length, output length is restricted to power 2. Okay, n is lower bounded by n min. So the minimum output length of the polar encoder can be 32. Okay, what am I saying here? The output of polar encoder, the minimum length can be 32. Okay, upper bound n max is 512 for downlink. Okay, so n max is 9 for downlink. Okay, is 10 for uplink. Okay, n max is, so the maximum encoder length can be basically 1024. You could ask this question, why? Why is it slightly higher than this? Because what happens in if you look at the uplink, okay, uplink user has lesser power than the base station. Okay, right? So typically what happens is user will encode it in the uplink, will encode this data at a lower rate than the downlink, so that base station is able to decode it, okay, at a lower SNR, which is typically observed in the uplink. Okay, because UE has lower power constraint than the base station. Base station typically transmits at higher power. You should understand that also, that the higher power at the base station is actually distributed amongst multiple users, because base station is transmitting multiple user data. Right? Okay. In the uplink, UE transmits only its own data. Correct? But the base station transmits the data of so many users, so that power is distributed. Even with that distribution, the downlink power each UE gets is higher than the user can use in the uplink. Okay, because they are typically battery constrained, and then user transmits at the lower power. Okay, typically 23 dBm, that's 250 milliwatt of power. Okay, and this is obvious for all the encoders that decoder complexity increases with n. That's why this restriction is there. Why not go beyond 20? Usual questions. Okay, so it's restricted because the decoding complexity increases with the encoder length. Right? Okay. Now, what is this? Another key aspects. Okay, and what is this aspect? Downlink maximum DCI length is 140. Right? Okay, and what is happening here? So the maximum length, the maximum is 140. Okay, it can go from 1, 2, 3 also. Okay, so you should note this. The polar codes are used when the DCI length is between 12 to 140. Okay, right? If this is length A is less than 11, the message is padded with zeros to reach A is equal to 12. Okay. Input message range for the polar encoder is between, what is this? For the polar encoder is between K to, what is this? A is 12 to 140. What is this K? You add 24-bit CRC to that. Right? So the K length is between 36 to 164. Fine? Okay. So that's the K. Okay. Right? Now, how to decide this polar encoder length? Okay. And you have to decide this, what length you should use. Okay. Right? So what is this? This N, how will you decide it? This n power, n is equal to 2 power n, that's the restriction, correct? Okay, and it has to be greater than or equal to capital K, because it cannot be less than the input which you are feeding. Okay, what are we doing here? I am deciding based on this K, what should n be? Okay, right? Of course, it is a function of the code rate also. Okay, right? And what are we saying here? So you calculate this n such that it is between n min and n max. Right? N min is how much? 5, and n max is 9 for downlink and 10 for uplink. Okay, right? And the code rate should be greater than 1 by 8. That you have to ensure. Okay, because the minimum is 1 by 8. You cannot pick an n which leads to a lower code rate than 1 by 8. Okay, these two conditions have to be met, because that's a practical constraint. 1 by 8, right? Polar decoder or polar encoder cannot decode at a rate lower than 1 by 8, right? Okay, and this constraint should also be satisfied, that the output length has to be such that this n lies between n min and n max. Okay, so let's see this. Okay, so the exact formula will come little later. Okay, what are we saying here? In uplink, maximum DC length is 1706. Okay, so polar codes are used for A between, if the A is between 12 to 1706. You see this, okay? The maximum DCI length, okay, right? It is 1706, okay, in the uplink. Okay. Now these polar codes are designed between this. What is the length? Okay, it is designed for these length only. Okay, so for A less than 11, what is you use some other codes. Okay, right? So in the uplink, what are we saying? The length is between 12 to 1706. Okay, and the length can be, this DCI length can be less than A also. And what kind of DCI you will get for that? It's an ACK or NAC. It's only 1 bit. Right? Okay, correct. Then what do you use? You don't even use the polar encoder. There are some other codes which are defined in the standard which are used for if the DCI is less than length A or less than 11. Okay. Now, what is this? Why is this 1706 and 140? Because typically the uplink, for the uplink, it has to carry this channel state information. Okay, right? And the channel state information contains many more bits. Okay, than the downlink DCI. Okay, that's why you see this. This is basically much more than that 140 number which is there for the downlink. Okay, right? So you'll see that for downlink and uplink, this DCI, even there are certain other blocks which are introduced, and one such block which is not there. Okay, what you would have missed now is basically there is no segmentation block. Okay, because the number of DCI bit is very small. Okay, you don't have to segment it. Okay, but for this uplink 1706. Okay, so it can be segmented, but the maximum number of segmentation block is only 2. Okay, we'll come back to it. Okay, but look at the key differences. What are we saying here? We have removed the segmentation block in one chain, right? Okay, because the DCI is small, so you don't need that. Don't have it. Okay, for the uplink, there will be a segmentation block which we are going to come back to. Okay, and there will be maximum of 2 such segmentation blocks. Okay, so what are we saying here? Okay, then to summarize, okay, the key ideas here are that the polar encoder, okay, is designed to create n virtual channels. Okay, and out of these n virtual channels, those k channels which have the maximum reliability, they are given to the message bits. Rest of the channels are given to the other parity bits. Okay, right? So that you get your message bits without any corruption. Okay, in the given SNR range where this polar encoder is going to work. Okay, right? And then we saw the polar encoder takes an n input and gives you n output. Okay, and just to get used to the notations or the terms in the standard, these n bits which we feed to the transformation matrix, okay, they are divided into index sets and the frozen sets. Okay, so the index sets will correspond to the channels which have the highest reliability, and frozen bits will correspond to the channels which have the least reliability. So what is happening? Okay, those, and what are those frozen bits? You are setting them to 0, right? Okay, they go through the most reliable channel, they'll give you the 0 output. Okay, they'll pass through the least reliable channel, they'll give you the 0 output. Message bits are going to pass through the most reliable channel and you'll get them as such. Okay, there are certain conditions which are enforced on this, on the design of this polar encoder, and these are the conditions which are enforced. Okay, so the maximum length is 512 for the downlink and 1024 for the uplink. Okay, right. So we'll stop here. We'll, in the next class we will discuss this code block interleaver. Okay, thank you.